Hi guys, welcome back to another past paper review video at Newton's Academy. Today we'll be looking at question 8. The diagram represents a galvanic cell. A small light bulb is connected in the external circuit and glows brightly. 8.1, state two conditions under which this cell will be a standard cell. Okay, so there's two conditions that apply to this specific cell. The first being that the temperature must be kept at 25 degrees Celsius or 298 Kelvin. The second is that the concentration of the electrolytes must be kept at 1 mole per dm3. 8.2, give the equation for the reaction which occurs at the Ag plus half cell, so the silver half cell. Okay, so how do we know whether it's going to be an oxidation reaction or a reduction reaction at that specific half cell? What we're going to do is we're going to go to our table 4b of standard reaction potentials, and we're going to compare the two metals in this case. So we're going to look at where Ag is and where Ni is on the table, and we're going to notice that Ag is much higher up than nickel, which means it has a higher oxidizing ability. Okay, and because it has a higher oxidizing ability, it's going to be reduced. Okay, I'll repeat that. Because silver is higher up on the table, it has a higher oxidizing ability than nickel, and therefore will be reduced. Okay, and we know how to write our reduction reaction. So it's going to be 8.2. So we're going to have Ag plus an electron to form Ag solid. Okay, 8.3, which electrode is the anode? Okay, so we're going to go back to our reasoning for the previous question. We said that silver is higher up on the table, therefore a greater oxidizing ability, therefore it's going to be reduced. And we know that reduction always occurs at the cathode. Okay, so that's something that's standard across them. The reduction will always occur at the cathode. And with that logic, it will of course mean that the other half cell will contain our anode. So Ni will then be our anode. 8.4, what happens to the EMF of the cell as it continues to deliver current? Of course, just like any other battery, we're going to have a decrease in EMF. Okay, so there's going to be a decrease in EMF. 8.5, write down the overall reaction for the cell. So in order to do this, we need to have the oxidation half reaction on its own and the reduction half reaction on its own, and then we're going to combine them. Okay, so we already have the reduction half reaction as written in 8.2. Let us go and write the oxidation half reaction. Okay, so we're going to have Ni to give us Ni2 plus 2 electrons. Okay, the next thing we're going to do is going to balance the number of electrons in each one. So in order to balance them, we're just going to times this entire equation by 2. Okay, so then we're going to have 2Ag plus 2 electrons to give us 2Ag solid. And then from there, the electrons will of course cancel out, and then we're just going to add the 2. Okay, so whatever is on the left-hand side of the arrow stays on the left-hand side. So you're going to bring down nickel plus 2Ag plus to give us Ni2 plus 2Ag. Okay, and that is our net overall expression. Okay, for the next question, it says if 0.4 moles of electrons flow to the cathode, what will be the decrease in mass of the anode? Okay, so I've already written out this answer, and what we're basically going to do is this. We're going to take the number. Okay, so they're speaking about the anode. The anode is of course relating to the nickel half cell. So if I just write that again, the nickel half cell is Ni to Ni2 plus 2 electrons. And they've given us so this is a completed balanced chemical reaction actually. So what we're going to do is we're going to take what they've given us, and we're going to try and use the molar ratio to get what we can use in a formula. So they've given us the number of moles for the electrons, so we can use the molar ratio to calculate the number of moles of nickel solid that has been now removed from that anode. And we use the molar ratio, and we get 0.2 moles of nickel. Okay, so that's the amount of nickel that has been removed. So it's the decrease in that anode. From there, we're going to use our formula. Mass is equal to number of moles times the molar mass. Okay, so again, we'll just bring down that 0.2, and the molar mass of nickel is 59. Okay, from there, it's just simple maths, and we get an answer of 11.8. Okay, so that's the decrease in mass. Question 8.7 states, a second galvanic cell B is constructed using magnesium and silver as well. Without any calculations, determine which of the two galvanic cells, A or B, will result in the highest potential difference. Explain your answer by referring to the relative strengths of the two reducing agents as well as the relative strengths of the two oxidizing agents involved. Okay, so what we need to understand here is that they're comparing the first galvanic cell, the one with nickel involved, to a galvanic cell with magnesium involved. Okay, so what I want us to understand is that the silver in both of them will have the same reduction potential. So it will have the exact same EMF involved with it. So what we basically trying to compare is the magnesium and the nickel. Okay, because the silver is something that's common in both, so it won't really affect it either way. So comparing the nickel and the magnesium is a better reducing agent than nickel, and it has a potential difference of negative 2.36 volts, while nickel has a potential difference of negative 0.27 volts. Okay, and of course the silver has the same oxidizing ability in both galvanic cells. Okay, so the answer here will be, of course, the second galvanic cell will have a great highest potential difference. Why? Because magnesium is a better reducing agent, and it has a higher potential difference than the nickel. Okay, so we've answered the entire question. We've made mention of the reducing agents and the oxidizing agents as well, and we've also made a little bit of reference to the potential difference in each one of them. Okay, so I hope this is clear.